right, folks, today we're looking at complex numbers. And complex numbers are basically numbers that have a real piece and an imaginary piece. So the first thing we want to talk about is this idea of imaginary numbers. And we've already maybe mentioned this a little bit, but just a refresher here. Remember, imaginary numbers are defined as the square root of a negative, okay? So the square root of negative 1 is defined as the imaginary number 1, okay? So numbers that result from the square root of a negative. And just a quick recap of those. So like here, if I took this square root of negative 64, the square root of a negative gives me an I. It's an imaginary I, imaginary number 1. And then the square root of 64 is an 8. So I would say here that this is an 8I, okay? Likewise, if I look at the next one, I would say, okay, the square root of a negative is an I. That gives me an imaginary number. And then the square root of 17, there's no perfect squares to divide into 17. So I leave that part as the square root of 17. So this is I root 17. Okay. Next one, same kind of thing. I take the square root of a negative, gives me an I. But then with an 18, there are perfect squares that divide evenly into 18. Remember, an 18 is really a 9 times 2. And when you think about a 9 times 2, you can take the square root of 9. That gives you a 3. But the 2 is still left over. Okay. And then this last one here, again, square root of a negative gives me an I, so I'm going to put the I on the outside. The 125, remember, perfect squares that go evenly into 125, that would be a 25 times 5. The square root of 25 is a 5, so I put a 5 on the outside. The other 5 is still left, so a 5 on the inside. And then remember, when I deal with the variables, I look at this as, hey, this is an index of 2. So when I do this, I divide the exponent, so 5 divided by 2. In other words, 2 goes into 5 twice, so an x to the second, with a remainder of 1, an x to the first left over on the inside of the radical symbol, okay? So just that recap of I. Anytime we take the square root of a negative, it produces this value of I because I is the equivalent of the square root of negative 1, okay? That's how it's defined. And so our big thing today is going to be dealing with these things that have i's involved in them, like complex numbers. But before we deal with complex numbers, we want to talk about simplifying powers of I, okay? I raised to a specific power. And so like this first one, I to the first power, well, anything to the first power is just that thing, so I to the first power is just I, okay? I to the second power, again, we've talked about this a little bit, but it's this idea that if I is really the square root of negative 1, this is like saying, hey, the square root of negative 1, that I'm going to square it, right? And what happens is the square and the square root cancel out, which just leaves me with the negative 1, okay? In other words, I squared has to equal a negative 1 just by the nature of what I is. If I is a square root of negative 1, squaring it would cancel out that square root. I'm left with a negative 1, okay? And now here's where things get really interesting. I to the third power, I want to start thinking about this in terms of previous powers of I. So instead of going back to that whole square root of negative 1 thing, let's just think of this as like I squared times I to the first. Like that's what I to the third is, right? Kind of breaking it up using my rules of exponents. And I already know from the previous question right here that I to the second is a negative 1. I already know from this question over here that I to the first is just an I. So what I have is negative 1 times I. In other words, I to the third ends up becoming a negative I. Likewise, if I do I to the fourth, I get using previous powers of I. You could break this down a couple different ways. I might say, hey, this is I squared times I squared. That's the same thing as I to the fourth, right? And so if we do that, I squared is actually a negative 1 times another I squared is also a negative 1. So when I multiply those two, negative 1 times negative 1 is a positive 1, okay? And so I'm just simplifying powers of I using previous powers of I. I to the first is I to the second is negative 1, I to the third is negative I to the fourth is 1. And I could keep that going. What becomes interesting now is because I've done so many of these, I have a lot of options to use. Like for this one, I could think of I to the fifth as I to the fourth times I to the first. And I to the fourth over here is a 1. I to the first is an I, so 1 times I, well, that's just an I. If I do I to the sixth, again, I could break it down a couple different ways, but probably the easiest one is I to the fourth times I squared. And I to the fourth is a positive 1. I squared is a negative 1, so what I have is positive 1 times negative 1, which is a negative 1. If I look at the next one, again, the easiest way to break this thing up would be I to the fourth times I to the third. Well, I to the fourth is a positive 1. I to the third is a negative I. Positive 1 times negative I is a negative I. And hopefully you're starting to see a pattern here. I to the fourth then, again, the easiest way to break this up is to say, hey, this is I to the eighth is to break this up into I to the fourth times I to the fourth. Well, I to the fourth is 1 times I to the fourth, which is also 1, and 1 times 1, which is going to give me a 1. This guy, I could use this idea that, this is an I to the eighth times an I to the first. And see, we're already back to I to the eighth, which is 1 times I to the first, which is I. So again, this one's going to give me an I. And you can probably guess that this is going to be a negative 1, and this is going to be a negative I. And I could keep doing that using my previous rules of exponents to find each of these, but I just have this pattern that emerges, okay? So every power of I is going to simplify to one of these 4 things. I, negative 1, negative I, or 1, okay? And the key to this pattern is the fact that it repeats every 4th exponent. Notice right here, I to the 4th, I to the 8th, I to the 12th. The next one that gives me a value of 1 is going to be I to the 16th, and then I to the 20th, and then I to the 24th. And so this idea is I'm looking for the closest I value that has a power of 4, okay, or power that's a multiple of 4, and I know that that's where the pattern ends. I know that one's going to be a positive 1 in the grand scheme of things. So if every 4th power of I is a positive 1, all I need to do is find those multiples of 4, and then I can kind of look at the pattern to figure out anything around that value. And that seems complicated, but it's really not that bad if I look at this first one here. I've got I to the 45th power. And keep in mind that any exponent here with an I that's divisible by 4, that's a product, that's a multiple of 4, is going to fall into that last column and is going to be a positive 1. And so for this one, I might look at the idea of, okay, so I to the 44th power, you see that that's going to have to equal a 1, right? I know that's not what I'm looking for. I'm not looking for I to the 44th. I'm looking for I to the 45th, but I notice that 45 is really close to a value that I know is divisible by 4. And so I to the 44th power is going to fall in this last category, right? Can you see that eventually we're going to get in this last row here, if I keep going, 16, 20, 24, 28, 32, eventually I'm going to get to 44. So I know that 44 falls here in the pattern, okay? And so it's this idea that if I kind of think about the pattern, it was I, negative 1, negative I, 1. I, negative 1, negative I, 1. I always do it like I'm chanting something. I, negative 1, negative I, 1. I, negative 1, negative I, 1. Okay? And so eventually we just get that pattern down. We know that, hey, if this right here is I to the 44, well, can anybody tell me what I to the 45th would be? Well, it's got to be the next one in the pattern. It's got to be right here. This has got to be just an I, okay? And so that's the idea. We want to kind of reset this thing based on a multiple of 4. And yeah, I'm going to put little dots on each end because this pattern just continues over and over and over again. I kind of orient it based on, okay, well, where is something that's divisible by 4 for the exponent, okay? I can do the same thing with the 87 here. Let me reset what I've got down here. So the closest value to 87 is probably 88, okay? So I to the 88th we know is going to have to equal a 1 because it's divisible by 4. So then I come down here and say, okay, well, that means that right here, use red this time, I to the 88th would be right here in the pattern, right? So think about where I to the 87th power would be. Well, it would have to be right here. It'd have to be the one before that, okay? So if I to the 88th is 1, the value before it must have been a negative I, okay? And so it's just pattern recognition and knowing that every power of I is going to simplify to one of these 4 things, okay? The next one, again, probably the closest value here, you could either do 116 or you could do the 120. It doesn't matter. Maybe I'll do the 116. I said that one first, okay? So again, down here, using my pattern, I would say, okay, I know that I to the, what did I just write here? I know that I to the 116th is going to equal a 1 just based on its exponent. So that means down here, I to the 116 would be right here. That means I to the 117th would be here. I to the 118th would have to be here. It's got to be a negative 1. If I look at the next one, again, 2,324, the closest one that's divisible by 4 here is 2,324. That one is divisible by 4, so that means there's no work to be done here. This one would be in that last column. That would have to equal a positive 1, okay? And hopefully you know the trick for determining if something is divisible by 4. You simply look at the last 2 digits. If the last 2 digits are divisible by 4, I was just looking at this 18, then the whole thing's divisible by 4. Here, the 24, divisible by 4, the whole thing's divisible by 4, okay? So again, you find the one that's divisible by 4, you know that has to fall into the pattern at the spot of 1. Well, now it's just a matter of counting a little bit forward or a little bit backward to see, okay, where is the value I'm looking for in terms of this pattern? Is it at I, negative 1, negative I, or 1, okay? So let's talk about complex numbers. Complex numbers are basically in this format, a plus bi, where a is a real number part and b, the bi is the imaginary number part, okay? And so that's why these are complex. They are kind of torn between two worlds, between real numbers and imaginary numbers, okay? And so we call them complex numbers because they have a real part and an imaginary part, all right? When we are doing, and the thing we're going to do here today is just simply doing operations with these these complex numbers, okay? And the thing is that when you approach this, you know, sometimes students get confused and think that this is just a variable, that I is just a variable. Well, that ends up being okay for about 90% of the problem, because when we treat these things as variables, we essentially do what we need to do, okay? So we're going to perform the operation as if I is a variable. We just have to then remind ourselves that I is not a variable. It's an imaginary number, and imaginary numbers can be simplified in terms of their powers, okay? And so really, I treat the thing like a variable. I perform the operations like it's a variable, but then I have to look for and simplify powers of I at the end, okay? Because the truth is that I is not a variable. It is a number, and it will always simplify using those powers of I we were just talking about, okay? To either I, negative 1, negative I, or 1, all right? So again, that's the idea here. I'm gonna just perform operations as if these were variables, but I have to keep reminding myself that they are not variables, they are imaginary numbers, and so anytime I have an operation like an exponent, I have to simplify that operation. Just like if I had 4 to the second power, I wouldn't leave it as 4 to the second power, I'd write it as 16. If I've got an I to the second power, I don't want to leave it as I to the second power, I want to write it as negative 1, okay? So making sure we simplify those powers of I because they are technically numbers, okay? For example, if I look at something like this guy, I'm adding 2 complex numbers, and if I were to treat this like I'm dealing with variables, it simply means, hey, let's combine like terms. Let's add up the like terms. Like I'm going to add the real number parts, 2 plus negative 3, which is a negative 1, and then I'm going to add the imaginary number parts, 5i plus 4i, which is a 9i. And there's not really anything else I can do. I can't add the real number part and the imaginary part. And not surprisingly, I added 2 complex numbers, and the answer I got was a complex number. It's got a real part and an imaginary part. And notice that I value can stay as just I. There's nothing that I can do to simplify that because there's no powers attached to it, okay? Really, the only big thing I can do with simplifying I is simplifying powers of I, okay? If I look at the next one, I'm subtracting 2 complex numbers. Again, just subtract the real parts. So negative 7 minus 2, which is a negative 9. And then subtract the imaginary parts, 3i minus a negative 6i, which is going to be a plus 9i. Again, there's not really anything else I can do there. There's no powers of I to simplify. That I value is as simplified as it can be. I just leave this as a complex number, okay? The place where we have to do a little bit more work is when we start multiplying these things. So if I look at this one, again, I'm going to use my distributive property. So I'm going to distribute this 3 to each of these. And when I do that, that gives me a negative 9 plus 12i. And now I'm going to distribute the 5i to each of these. And when I do that, that gives me a negative 15i plus 20i squared. And then from here, it's just a matter of simplifying, okay? I continue to simplify anything that I can simplify. So like here, I can simplify by combining these like terms, okay? They're both imaginary numbers. I can combine those imaginary numbers. That gives me a negative 3i. But then right here, this is where we have to be very careful. If this was a variable, I would just leave it as I squared, but it's not a variable. That is a number, and I squared can be simplified using powers of I. Well, I squared is a negative 1. In other words, what I have here is 20 times negative 1. And if I do 20 times negative 1, that gives me a negative 20, so I have to slap down a negative 20 here. I was able to simplify that using powers of I, okay? And now I have more like terms to combine, the negative 9 and the negative 20. So all said and done, this is going to be a negative 29 minus 3i, okay? And again, it's not surprising that I multiplied two complex numbers and I got another complex number. Will that always happen? No. There's certainly times where a complex number times a complex number will give me a real number. It's a pretty fun magical thing that happens, and maybe we'll see one of those coming up shortly. Spoiler alert. If I look at this next one again, I'm going to do my distributive property, so I'm going to distribute the negative 7. That's a negative 35 plus 42i. Distribute the the 3i. That's a 15i and a minus 18i squared. And once again, I just have to simplify from here. I'm simplifying by combining like terms. I'm simplifying powers of I. And so for this one, I combine those like terms in the middle, those two imaginary numbers. That gives me a 57. And then once again, this guy over here, I squared, is actually a negative 1. And so if I have a negative 1 and a negative 18, that's multiplication. That's going to be a plus 18 at the end of this thing. And now I have more like terms that I combine. I can combine that negative 35 and the positive 18, and that gives me a negative 17 plus the 57i. Okay? But again, it's all about just simplifying. And yes, I run into these powers of I that have to be simplified more and more and more. Okay? If I look at the next one, again, when I'm squaring a binomial like this, remember you have to multiply that thing by itself. I can't just square each piece. Multiplying this binomial times itself means I have to do the 3 plus 4i times 3 plus 4i, okay? And complex numbers by nature are binomials, essentially. So we want to approach them that way because they're binomial in nature, all right? So when I square that thing, I can't just square each piece. I got to do that thing times itself. Now I have to do my distributive property, okay? So I'm going to distribute the 3. That gives me a 9 plus 12i. I distribute the 4i, that gives me a 12i plus 16i squared. And now from here, it's just a matter of simplifying. I've got some like terms in the middle. That's a 24i. Once again, that value at the back end here, right here, this is a negative 1. So that's going to give me a minus 16 on that back end, okay? So again, I just have to simplify those powers of I. Now I have more like terms that I can combine, and that gives me a negative 7 plus 24i. Okay? And yeah, I've cut out a little bit of work each time. I've been showing a little bit less in terms of that power of I as we've gone to do a little bit more in my head. You can show those steps a little bit more meticulously or cut a little bit of that out as you go. That's kind of up to you, all right? If I leave this last one, again, I've got conjugates this time, and we already know the special thing that happens with conjugates, but let's see it in action here. So I distribute the 2. That's going to give me a 4 plus 6i. I distribute the negative 3i. That's a minus 6i, and then a minus 9i squared. And again, the special thing that happens is those like terms in the middle, the 6i and the minus 6i, cancel out completely. That's the nature of conjugates, what always happens. But then the thing that's really special right here is I've got that I squared will simplify to a negative 1. And so once again, if this guy right here is a negative 1, it means what I have is a 4 plus 9, because the negative 9 times the negative 1 is a positive 9. Well, this just gives me a 13. And that's a really interesting special case because I went from having two complex numbers to having an actual real number for my answer. And that goes back to what imaginary numbers are. By nature, imaginary numbers are radicals, right? An imaginary 1 is the square root of -1. And we already know that when we multiply binomials that are conjugates, when I'm dealing with radicals, the special thing that happens is that all the radicals go away. So if I is essentially just a radical, yeah, multiplying by the conjugate will make all the i's go away as well. Okay, so again, the idea here is powers of I are kind of based on that pattern recognition. It's I -1, -I1. Okay, and the whole pattern hinges on, okay, what's the what value has a multiple of 4 for the exponent? I fix that at the 1, and then I count through the pattern from there to find any power of I need. And then complex number have the real number part, the imaginary number part. We treat them like variables, but we have to simplify, including powers of I, including combining all my like terms. Okay?